In this first problem, a cleat on a boat is used to support forces from 3 ropes as shown. We want to determine the resultant force vector r using a Cartesian representation and also determine the magnitude of r. You should pause the video now and try this problem yourself. Resume playing when you are ready to see one solution. We can write an expression for the resultant by collecting all the I and j components independently. Before we do that, let's just make a note based on the visual inspection of this figure what we expect in terms of positive and negative components for each force. Forces F2 and F3 are in the first quadrant, so we expect them to have both positive x and y components. Force F1 is in the second quadrant, so we expect it to have a negative x and a positive y component. Note also we have 3 different ways of representing the angles. For F1, we have an angle defined off the vertical axis, which means that the sine of that angle will give us x component information, and the cosine of that angle will give us y component information. For F2, we have the rise over run that's given as 12 over 5, and this is one of these special triangles. If we have a run of 5 units and a rise of 12 units, we can show that the hypotenuse here will be 13. So we don't actually need to find this angle. What we can say right away is that the cosine of this angle that I'm representing here would be 5 over 13, and the sine would be 12 over 13. And finally, we have in F3 an angle defined off the x-axis. So in writing our expression for the resultant and collecting all the I terms first, we have 400 sine 40 degrees as the x component magnitude of F1, but it's in the negative x direction, so we'll write it as minus 400 newtons sine of 40 degrees. And then for F2, we have plus 200 newtons times the cosine of the angle of inclination with the x-axis, but we said that that's 5 over 13, plus 100 newtons cosine of 30 degrees, and all of that is in the I direction. In the j direction, we have 400 newtons cosine of 40 degrees for F1. We have 200 newtons times the sine of the angle of inclination with the x-axis, which we said was 12 over 13. And then finally we have 100 newtons times sine of 30 degrees for F3, and all of this is in the j direction. So evaluating those terms, we end up with a result for r which is minus 93.59 I plus 541 j newtons. The magnitude of the vector we get from just the square root of the sum of the squares, and that turns out to be dominated by the j component, and that ends up being 549 newtons. Now we can see from this result that our resultant has a small negative x component and a relatively large positive y component, which means that the resultant is in the second quadrant and should be reasonably close to 90 degrees. Now we can, if we wanted, we can find a representation for this as a polar representation. We could define an angle off the x-axis as the arctangent of the ratio of the y and x components. So we have arctangent 541 over minus 93.59, and if we just plug that into our calculator, it will give us a value that's actually in the fourth quadrant. It will be minus 80.19 degrees, but because we can see where the resultant ends up, we know that we actually have to add 180 degrees onto that, and we end up with a value here that's 99.81 degrees. So our final result, either in Cartesian components we have as it's shown here, or we could also say that it's equal to 549.0 newtons at an angle of 99.81 degrees to find counterclockwise off the x-axis. For our second example, we have a motor-driven gear used to produce forces P1 and P2 in members AB and AC of a machine. Member AC is parallel to the y-axis. We want to determine the x and y components of the resultant force vector at A due to forces P1 and P2, and then determine the tangent and normal components of the resultant force vector. At this time, you should pause the video and try to work through this problem yourself, then resume playing when you're ready to see one solution. Again, before we begin, we should just make a note of the directions that P1 and P2 point and our expected contributions from those forces in the x and y directions. Force P1 has a line of action that's pointing down and to the right, so it's going to be in the fourth quadrant, and we expect it to have a positive contribution in x, but a negative contribution in y. Force P2 is pointing straight down, so it's actually straddling the third and fourth quadrants, and it will just give us a negative contribution in y. We can write an expression for r as having, in the x direction, we have just a contribution from P1, and so that's going to be 200 pounds cosine of 30 degrees along I, and then both contributions from P1 and P2 are negative in J, so I'm just going to bring the minus out in front here and say we have a 200 pound sine of 30 degree component from P1, and then plus 50 pounds from P2, again both in the minus J direction. And if we evaluate that, we end up with a resultant which is 173.2 pounds in I minus 150 pounds in J. For reference, we can find the magnitude of this vector as the square root of the sum of the squares, and that value turns out to be equal to 229.1 pounds. Now the second part of this problem is a little less obvious because our tangent normal system is rotated with respect to the xy system. So to begin, I'm going to slide P1 along its line of action and draw it here at A. And just make a note that we've got two different 30-degree angles here. We have that P1 makes an angle of 30 degrees with the horizontal below, and the normal axis makes an angle of 30 degrees with the x-axis, so all of that means that this angle is going to be 60 degrees. And if we slide P2 down, we have that this angle here is 30 degrees. So what I'm going to do is resketch this now with the normal tangent system rotated so it's a little bit easier to see this. So here we have a resketched representation of P1 and P2 in the tangent normal system. And we can see that P1 is going to have positive components in both normal and tangent directions. P2 will have a positive component in the tangent direction and a negative component in the normal direction. So we can say now that the resultant is equal to, in the tangent direction, we have P1 sine of 60 degrees and we also have P2 cosine 30 degrees. In the normal direction, we have P1 cosine 60 degrees and P2 sine 30 degrees, but in the minus normal direction. And if we plug in 200 pounds for P1 and 50 pounds for P2, we end up with 216.5 pounds in the tangent direction and plus 75 pounds in the normal direction. One check on whether or not we've done this correctly is to find the magnitude of this resultant in our tangent normal system. The magnitude of the resultant shouldn't depend on whether we represent the force in an xy coordinate system or a tangent normal system, so we should have the same resultant. And here r would be the square root of the sum of the squares again, and you can verify that if we do that, we once again get 229.1 pound.